Right. Hey, everyone. You ever get those like really weird thoughts late at night?
Oh, yeah, all the
Like
time.
something you might have seen in a sci-fi movie or read in like, some really intense book.
Yeah.
It's like one of those thoughts has been bugging me.
Okay.
It's this idea about, um, could an astronaut,
Hmm.
like if they fell into a black hole,
Okay. Yeah.
could they actually see the entire future of the universe?
Whoa.
Like in a blink of an eye?
That's
It sounds completely insane.
yeah, no, it's a fascinating idea.
It's like something straight out of like a Philip K. Dick story or something.
Right.
I think even like Stephen Hawking has talked about it.
Yeah, I think it comes up a lot in discussions about black holes for sure.
Yeah.
It's definitely one of those mind-bending concepts that really captures the imagination.
Exactly.
So are we going to try to figure out if this is actually true?
That's exactly what we're doing today.
All right, I'm in.
This is our deep dive
Nice.
into whether or not that wild idea actually holds any water when you look at the real physics.
Awesome. Let's get into it.
Okay.
I'm excited.
So we're going to be checking out some pretty serious physics research and a few books
Okay.
to kind of guide us along the way.
Sounds good.
It'll be like getting a crash course on how black holes work,
All right.
according to Einstein's general relativity.
Perfect. That's the framework we need.
And to make things even more interesting, we're going to be looking at this from two totally different points of view.
Oh, absolutely. That's key to understanding this whole thing.
Okay, so first we're going to imagine
Yeah.
we're like way out here on Earth, just watching this astronaut,
that.
take a plunge into a black hole.
Right. I'm picturing it.
And then we're going to try to wrap our heads around
Yeah.
what it would be like from the astronaut's perspective
From their point of view.
as they approach.
Right.
And maybe even cross over that point of no return.
That event horizon? Yeah.
That's really the heart of this question.
It is. It's like, how can these two perspectives even coexist?
Yeah.
One where they seem to freeze in time and another where they just keep falling.
Exact.
So how do we even begin to tackle this?
Well, we've got some really good sources to help us out.
Let's hear it.
So we've got this research paper,
Okay.
and it's called, and get ready for this title, Is It Possible to See the Infinite Future of the Universe When Falling into a Black Hole?
Wow, they just cut to the chase, don't they?
I know, right?
Who are the authors?
It's by A.A. Grib and U.V. Pavlov.
Interesting. I'm not familiar with their work specifically, but I'm sure it'll be insightful.
And then, to make sure we've got all the basics covered, we're going to be referring back to the standard textbooks on general relativity.
The classics, right?
Yeah.
Like Landau and Lifshitz.
Exactly, the ones that lay out the foundation.
The groundwork, yeah.
And then we'll also be looking at how this whole idea about seeing the future, how that gets presented in popular science books.
Oh, yeah. Those are important, too, because they really shape how people understand these things.
Yeah, exactly.
There are some really good ones out there.
Yeah, like,
I mean, you mentioned Stephen Hawking.
oh yeah, Stephen Hawking, of course.
He wrote some very accessible stuff.
And then there's A.M. Charapashchuk
Right.
and T. Reg.
Yes, they've all tackled this concept in their own ways.
And then we've also got some really essential stuff from I.D. Novikov and V.P. Frolov.
Oh, they're giants in the field of black hole physics.
And, of course, S. Chandrasekhar.
Ah, his work on stellar evolution and black holes is absolutely fundamental.
So, yeah, we've got like a pretty good lineup of sources here.
We're well equipped for this deep dive.
Okay, so let's get into it.
Let's do it.
So imagine like the most basic type of black hole,
Right.
a Schwarzschild black hole.
Okay, so non-rotating, no electric charge.
Exactly, just like pure gravity.
The simplest kind,
Yeah.
but still incredibly complex.
Oh,
All right, so we're picturing our astronaut heading towards this black hole.
yeah. And remember, we're going to thinking about this from two different points of view.
Right, that's crucial.
So first, let's imagine
Okay,
we're like, safely back here on Earth.
distant observers.
And we're watching this astronaut
Got it.
fall towards this black hole.
Okay.
Now, according to general relativity,
Yeah,
as they get closer and closer to the event horizon,
a point of no return,
the Schwarzschild radius,
that boundary.
something really strange starts to happen
Let's hear it.
to us. From our perspective here on Earth,
Yeah.
the astronaut will appear to slow down. And I mean, like, really slow down.
Like they're hitting the brakes.
It's like they're approaching a complete stop,
Just as they reach the edge?
right at the edge.
Almost like they're frozen in time.
Yeah, it's like a movie that gets stuck on pause right before the climax.
That's a great analogy. They never actually seem to cross over from our point of view.
It's like they're trapped on that cosmic pause button forever.
And that, my friend, is the power of time dilation.
Time dilation.
It's like their time is being stretched out.
Compared to our time here on Earth.
Exactly. It's becoming almost infinitely long relative to our own clocks.
It's like they're entering a whole different time zone.
Yeah. One where time practically stands still.
But here's the really mind-bending part.
Okay, I'm ready.
Now we got to shift perspectives and try to see things from the astronauts' point of view.
All right, let's get into their shoes.
From their own experience.
Yeah.
Now, according to their own clock.
What we call proper time in physics.
Right, just like the time on their own wristwatch.
Mm-hmm.
They will actually fall through the event horizon.
No way, really.
In a finite amount of time.
So no infinite slowing down for them.
Nope, they just cross it.
Like it's not even there.
That's where things get super weird.
That's a huge discrepancy between the two perspectives. One says they freeze, the other says they fall right through.
And it's not just like, a matter of opinion.
It's a fundamental question about how we understand reality.
Yeah, there's a physicist named Yuval Ne'eman.
Okay.
And he actually pointed this out.
Hmm. What did he say about it?
He was like, how can both of these things be true at the same time?
Yeah, how can we reconcile these two seemingly contradictory viewpoints?
It's like, if, from our perspective, they never cross over, how can they have their own experience of being inside?
It's like we're dealing with two different realities.
And he actually called this a kind of surrealism.
Surrealism, I like that.
Yeah, it's like these two realities existing side by side.
But somehow incompatible.
It's a bit of a head scratcher, isn't it?
It is, and it really highlights the limitations of our everyday intuition when trying to grasp these extreme cosmic phenomena.
So I guess the question is, how do we even begin to make sense of this?
Well, the paper hints at a resolution.
Okay.
It suggests that our Earth-based view, while valid in its own right, is incomplete.
Incomplete, like it's missing something.
It can't fully describe what happens inside the black hole.
Ah, I see.
We need a more comprehensive picture.
Okay.
And that's where the astronauts' experience, along with more advanced ways of mapping space and time, comes in.
Okay.
Like, have you heard of Kruskal-Sekker's coordinates?
Kruskal-Sekker's coordinates.
It sounds intimidating, but it's essentially a different way of charting space and time.
Like a different kind of map.
Exactly. Yeah. And this map is smoother. It avoids those roadblocks we encounter with our usual way of thinking.
So it can describe both the inside and the outside of the black hole.
Precisely. And it shows that the time felt by the astronaut inside isn't directly connected to our time in a simple way.
Okay, so their time is kind of its own thing.
Yeah, there's a mathematical breaking point, a singularity, if you will, when we try to translate between these viewpoints right at the horizon.
All right, so let's get to the heart of our original question.
The big one, yeah.
This idea that as the astronaut gets closer and closer to the horizon, they'd start to see the whole future of the universe unfold in front of them.
Like a fast-forward button on the cosmic scale.
Exactly. They'd see the sun burn out.
The Earth crumble.
All the galaxies drift apart.
A whole cosmic show condensed into a few brief moments.
Yeah. It's a really powerful image.
It is. It really captures the imagination.
And our sources actually point out that this idea has really captured the imagination of a lot of popular science books.
Right. It's a common theme in those kinds of books.
But here's the thing.
Okay.
The physics described in our sources actually disputes this.
They argue against it.
Yeah, they're like, no, that's not really how it works.
So why not? What's the physics behind that?
So the paper, the one by Grib and Pavlov.
Okay, yeah.
They use something called the Schwarzschild metric.
Ah, the Schwarzschild metric. That's our tool for understanding the geometry of space-time around a non-rotating black hole.
Yeah, it's like a way of writing down the rules of space and time.
In that region, exactly.
So what does this metric tell us about the astronaut's journey?
Well, it helps us analyze the paths of both the astronaut and the light rays that they might see.
Okay, so the astronaut's path, we already talked about that.
Right. They fall in a finite amount of their proper time.
But what about the light coming from the distant universe?
That's where things get interesting.
Could that light still be reaching them at like a super accelerated rate?
Because they still see those eons unfold in an instant?
Yeah, like even though their own time isn't stretching out forever.
Right.
Could the light from the outside still be showing them the far future?
It's a good question, and the answer, unfortunately, is no.
No.
The paper shows that while the travel time of light rays from a distant point to the falling astronaut does increase as they approach the horizon, it doesn't become infinite in a way that allows them to see an infinite duration of external events before crossing over.
Okay, so time is definitely being stretched out for them from our perspective.
Absolutely. That part's still true.
But the amount of stretch time they can actually see before they cross over is still limited.
Precisely. It's not like an endless movie reel of the universe's future.
So no infinite future insights in those final moments.
Sadly, no.
Okay, what about this idea?
Yeah.
Like, instead of falling straight in,
Mm-hmm.
what if the astronaut somehow managed to hover or
Mm.
orbit really close to the black hole?
Like right at the edge?
Yeah. Could they potentially see more of the future that way?
Because of that extreme time dilation near the event horizon?
Exactly.
A clever idea, but it doesn't quite work out.
No, not.
Well, the paper touches on this briefly.
Okay.
And they point out that even though time dilation would be significant in such a close orbit, it wouldn't be enough to allow them to see the infinite future.
Still not enough.
And there's another problem.
What's that?
Those kinds of orbits, the ones really close to the black hole, are actually unstable.
Oh, so they couldn't stay there for very long anyway.
Exactly. Anything that gets that close is pretty much doomed to fall in.
So no hanging out at the edge to get a glimpse of the end times.
Nope. The universe doesn't work that way.
All right, so what happens when the astronaut actually crosses the event horizon?
That's where things get even weirder.
Does the picture change once they're inside?
You see, the Schwarzschild metric we've been talking about, it kind of breaks down at the event horizon.
It breaks down.
It becomes problematic, yeah.
So it can't really describe what's going on inside.
Not in a straightforward way, no.
Okay, so what do we do then?
We need a different tool.
A different tool, like what?
It's called the Kruskal-Sekaras coordinate system.
Kruskal-Sekaras.
Yeah, it sounds like something out of Star Trek, but it's a more sophisticated way of mapping space and time around a black hole.
So it's like a better map that can handle what's happening inside.
Exactly. It smooths out those wrinkles we encounter with the Schwarzschild metric.
Okay, and what does this new map tell us about seeing the future once you're inside the black hole?
Well, even inside the event horizon, as the astronaut is falling towards the singularity, the central point of infinite density, their causal past remains limited.
Causal past. That's like all the events they could possibly have seen.
Exactly, and it's limited even inside the black hole.
So even after they cross over, they still can't see the infinite future.
Nope. The light rays from those distant future events just can't catch up to them in time.
So the infinite future is still out of reach.
Even inside the black hole.
All right, so for a static black hole, the answer seems pretty clear.
No infinite future sightseeing allowed.
But what about those more complex kinds of black holes?
Ah, you're talking about the rotating ones?
Yeah, and the ones with an electric charge.
Like the Kerr, Reisner, Nordstrom, and Kerr-Newman black holes.
Exactly. Do those offer any loopholes in this cosmic law?
They do introduce a fascinating twist, something called the Kachi horizon.
The Kachi horizon.
Yeah, that's another boundary inside the black hole.
Another one. So there's the event horizon and then the Kachi horizon.
Yeah, it's a bit more complicated.
Okay, so what's so special about this Kachi horizon?
Well, theoretically, an astronaut crossing this horizon might, in a fleeting instant, witness the entire history of the external world.
Whoa, hold on. The entire history, like the past and the future?
Theoretically, yeah.
How is that even possible?
It's due to an effect called infinite blue shifting of light.
Infinite blue shifting.
It's kind of like when a train is speeding towards you
Ah.
and its whistle sounds higher pitched, but with light.
So the light waves are getting compressed.
Exactly. And infinite blue shifting means those light waves are squished to infinitely high frequencies.
As the astronaut approaches this Kachi horizon.
Right. It's like the whole future history of the universe gets packed into that single moment of crossing.
So maybe there is a way to see the infinite future after all.
Well, there's a catch, a pretty big one.
Okay, I'm guessing it's not that simple.
That infinite blue shifting also implies an equally infinite concentration of energy.
Infinite energy, that sounds dangerous.
Yeah, it is. And our sources point out that such a huge amount of energy would likely distort space-time itself.
So it could create a singularity right there at the Kachi horizon.
Exactly, a cosmic bait and switch.
It's like the very thing that might allow you to see the future
Yeah,
could also destroy you in the process.
it's a classic cosmic trade-off.
And to make things even more complicated, real black holes aren't perfectly isolated.
Right, they're constantly interacting with their surroundings.
Yeah, like they're subject to disturbances like gravitational waves
Ripples in the fabric of space-time.
and matter falling into them.
Yeah, all sorts.
And when you take those things into account,
Yeah.
the Kachi horizon might not even be a smooth surface.
It could become singular itself.
A singular Kachi horizon.
Yeah, either a weak or a strong singularity.
And I'm guessing neither of those is good news for our astronaut.
You'd be right. A strong singularity would likely rip them apart.
Due to those intense tidal forces.
Exactly. And even with a weak singularity, the chances of survival are slim.
So, seeing the infinite future at the Kachi horizon.
Yeah.
It's highly uncertain.
And probably not a very pleasant experience.
All right, so let's try to summarize all of this.
Okay, good idea.
We started with this really intriguing idea of witnessing the entire future while falling into a black hole.
The ultimate cosmic preview.
Based on our deep dive into all this physics research,
Yeah.
what's the verdict?
Well, for a simple, non-rotating black hole like the Schwarzschild black hole, the answer is pretty clear. The popular notion of seeing the infinite future just doesn't hold up.
It's busted.
The astronaut's own time is finite.
And the amount of light, and therefore information they can receive before crossing the horizon, is also limited. What about those more exotic black holes, the rotating and charged ones?
Well, with those, things get a bit more complicated.
Yeah.
The Kashi horizon does introduce the theoretical possibility of seeing the entire history of the universe in a flash, but it comes with a lot of caveats.
Like the potential for being destroyed by infinite energy.
Yeah, and the fact that real black holes are subject to disturbances that could make the Kachi horizon itself singular.
So it's still a very open question.
Definitely an area of active research.
It's amazing how the reality, as we understand it through physics, is both more complex and in some ways less exciting than those wild sci-fi scenarios.
I know, right?
But in a way, what we've uncovered is even more mind-blowing.
Absolutely.
This idea that different observers can have such drastically different experiences of reality.
Like the astronaut and the distant observer.
And the strange way that space and time switch roles inside a black hole.
That's really hard to wrap your head around.
It's like those concepts we take for granted.
Like up and down, past and future.
They just don't apply in the same way near a black hole.
It really challenges our fundamental understanding of the universe.
And, you know, that point about different realities being understandable, even if we can't fully imagine them.
Yeah, I like that.
It makes me think that maybe there are other aspects of the universe that are just as bizarre and counterintuitive.
Things we haven't even begun to imagine.
And maybe our current understanding is just a tiny glimpse.
A small window into a much grander and weirder reality.
So, as we wrap up this deep dive, here's a thought to leave you with.
Okay.
If even something as seemingly well-defined as a black hole still has these mind-boggling complexities.
Like the Kachi horizon and different types of singularities.
What other seemingly settled ideas in physics might be hiding even more surprising secrets?
It's a great question.
Like maybe our current understanding is just the tip of the iceberg.
And there's a whole universe of weirdness waiting to be discovered.
Something to ponder, wouldn't you say?
Definitely something to keep me thinking.
All right, well, thanks for joining us on this deep dive.
It's been a fascinating journey.
And until next time, keep exploring the cosmos.
And keep asking those big questions.
Because who knows what other amazing things are out there waiting to be discovered.
Yeah, the universe is full of surprises.
And that's what makes it so incredible.
Absolutely.